So let's take a look at Lagrange multipliers. So let's say we have a multivariable function, f of x, y, and then we have a constraint. And the constraint is always going to be in the form g of x comma y, so some multivariable function, and that's going to be equal to a constant. Now what Lagrange multipliers help us do is they help us find maximum minimum values for a multivariable function in the given constraint. So for these next set of problems, we have to use Lagrange multipliers to find the maximum and minimum values of the function subject to the given constraints. So for number one, the multivariable function f of x, y equals x squared times y, and the given constraint here is that x squared plus 2y squared equals 6. So once again, we have to find the maximum and minimum values of the given multivariable function in the given constraint. So realize that x squared plus 2y squared is that one constraint, which is in the form g of x comma y equals some constant, and that constant is going to be 6 this time. So since we have two variables here, x and y, we need to create a system of equations, and we need two of those, one for x and one for y. So the equation here, the first one for x is going to be f sub x equals lambda times g sub x. And the second one follows the same rule here, f sub y is going to be equal to lambda times g sub y. So let's go ahead and first find f sub x, or in other words, the partial derivative of the function with respect to x. So if x is the variable, y is the constant, then the partial derivative of x squared y is going to be 2xy. And that's going to equal lambda, the variable, times g sub x. So we're going to take the partial derivative of g with respect to x. So the partial derivative is simply just 2x. So if we go ahead and simplify, the 2x's will cancel, and so we'll get y equals lambda. So now let's solve the next equation here, f sub y. So the partial derivative of the function with respect to y is going to be x squared. Since y is the variable, x is going to be a constant. That's going to equal lambda times g sub y. So the partial derivative of our g function with respect to y. Derivative of x squared is 0, derivative of 2y squared is positive 4y. Now since we have two variables here, what I'm going to actually do is take what I found from the first equation, that lambda equals y, or y equals lambda, and go ahead and substitute that in. So what I'm going to actually do here is replace y with lambda, so then we get x squared equals 4 times lambda squared. So now we can substitute both of these equations into the given constraint. So notice x squared does equal 4 lambda squared, so I'm going to replace 4 lambda squared with x squared. So we get 4 lambda squared plus 2y squared. Now y equals lambda. So if I replace y with lambda, we'll get 2 lambda squared. That's going to equal 6. So then 4 lambda squared plus 2 lambda squared is 6 lambda squared. That's going to equal 6. So go ahead and divide over the 6's. Lambda squared equals 1. Then lambda will equal plus or minus 1. So now what we need to do is we need to find the x and y values in two different scenarios. The first scenario is when lambda equals 1. And the second scenario is when lambda equals negative 1, since our answer is both lambda equals plus or minus 1. So let's go ahead and first solve this bottom x equation here and solve for x. So if x squared equals 4 lambda squared, x will equal plus or minus the square root of that, or in other words 2 lambda. So if I go ahead and replace lambda equals 1 into that equation there, we'll get x equals plus or minus 2. Now if I go ahead and replace lambda equals 1 into the y equation, obviously y equals lambda, so that means y equals 1. So now let's go ahead and replace negative 1 for lambda. If that's the case, then x will equal plus or minus negative 2. Now plus or minus negative 2 is the same thing as saying plus or minus 2, so we go ahead and replace it with that. If I go ahead and replace it for the y equation, y equals lambda, so if lambda equals negative 1, then y is also going to equal negative 1. So if I go ahead and write it in coordinate pairs, when lambda equals 1, we then have the coordinate pair of x is plus or minus 2, so that's the x coordinate, and the y coordinate is 1. And then when we have lambda equaling negative 1, then we have the coordinate pair, once again plus or minus 2, and this time negative 1. So now the last step is to plug both of these coordinates into the original function, and then find the maximum and minimum values. So notice that the x value is squared, so it doesn't matter if the x is plus or minus 2. When we square it, it's going to be positive. So if I go ahead and plug in plus or minus 2, 1 to the original function, we'll then get 2 squared, which is 4, times 1, so we'll get 4. And then if I plug in plus or minus 2 negative 1 to the original function, we'll get 2 squared, which is 4, times a negative 1 this time, so negative 4. So now given this information, we can conclude that negative 4 is going to be the minimum value, and then 4 will be that maximum value. So maximum value, once again, when we plugged in f of plus or minus 2, 1 into the original equation, or into the original function, and then we got the minimum when we plugged in plus or minus 2, negative 1 into the original function. So now for number 2, we have f of x, y, z equals x times y times z, and the given constraint is x squared plus 2y squared plus 3z squared equals 6. So notice we have 3 input variables here, x, y, and z, so we have to create 3 equations this time. And so once again, f sub x will equal lambda times g sub x, f sub y is going to equal lambda times g sub y, and then f sub z this time, it's going to follow the same exact rule, will equal lambda times g sub z. So let's go ahead and first find f sub x, or the partial derivative of the function with respect to x, which is going to be y times z. And so y times z will equal lambda times g sub x. So the partial derivative of this function with respect to x, and so that's going to be 2x. So in this case, I would recommend solving for lambda. So in this case, lambda will equal yz over 2x. And so I'm going to stop there and then move on to the next equation and solve that one. So f sub y is going to be the partial derivative of the function with respect to y, which is x times z. That's going to equal lambda times g sub y. So that's going to be 4y to the first. So if I go ahead and solve for lambda once again, lambda is going to equal xz over 4y. And then we'll move on to the last equation here. F sub z is going to equal x times y. That's going to equal lambda times g sub z, which is going to be 6z to the first. So we'll go ahead once again, solving for lambda equals x times y over 6z. So now what I can do is, since all of these equal lambda, I can go ahead and first set these two equations equal to each other. So we get y times z over 2x equals x times z over 4y. So if I go ahead and cross multiply here, we then get 4y squared z equals 2x squared z. So notice if I can cancel out the z's from both sides. So then we'll get 4y squared equals 2x squared. So then if I divide over the 2, we'll then get 2y squared equals x squared. So I'm going to go ahead and leave 2y squared equals x squared just like that for a second. I'll come back to it. So now I'm going to set these two equations equal to each other. So we get xz over 4y equals x times y over 6z. So if I go ahead and cross multiply, we get 6x times z squared equals 4x times y squared. Notice the x's will cancel since they're on both sides of the equation. So then we get 6z squared equals 4y squared. So I go ahead and divide both sides by 2. We get 3z squared equals 2y squared. So now, looking up at this constraint equation here, notice that x squared equals 2y squared and that 3z squared equals 2y squared. So I'm going to go ahead and plug in or substitute in both of those. So x squared is 2y squared, so 2y squared plus, we'll leave 2y squared just like that, plus another 2y squared is going to equal 6. So then this time 6y squared equals 6, y squared equals 1, so then y is going to equal plus or minus the square root of 1 or plus or minus 1. So now using the information that y equals plus or minus 1, I can go ahead and plug into both of these equations to find what x and z are. So let's go ahead and plug it into this equation first. So 2y squared, so 2 times plus or minus 1 squared is just going to be 2 times 1, which is 2. If 2 equals x squared, then x will equal plus or minus the square root of 2. So now let's go ahead and plug in y into this equation. So then 2y squared, once again, 2 times plus or minus 1 squared is 2 times 1, which is 2, equals 3z squared. Z squared was going to equal 2/3. So then z will equal plus or minus the square root of 2/3. So the last thing we need to do is plug in all these values into the original function and try to find the maximum and minimum values. Now before we do this, we need to come up with an ordered pair that can lead us to the maximum value and can also lead us to the minimum value, since we have both plus or minus here. So if we make all these positives, let's say we have plus or positive square root of 2, positive 1, and a positive square root of 2/3. If we plug these values into the original function, this will lead us to the maximum value. So if we plug in f of this coordinate pair, now if we plug in f of all negatives, notice 3 negatives will still be a negative. That will lead us to the minimum value of the function when we plug this in. So negative square root of 2, negative 1, and negative square root of 2/3. So let's go ahead and plug these into the original function to see our what our maximum minimum values are. So let's go ahead and first plug in square root of 2, 1, and square root of 2/3. So we get x times y times z, which is square root of 2 times 1 is square root of 2, times, now I'm going to rewrite square root of 2/3 as square root of 2 over square root of 3. So square root of 2 times square root of 2 is 2, so then we get 2 over square root of 3. Now if we plug in this one here, negative square root of 2, negative 1, and negative square root of 2/3, we will then get x times y, so we'll still get square root of 2, but this time times a negative square root of 2 over square root of 3. So then we'll get negative 2 over square root of 3. So this will be our maximum value, 2 over square root of 3, and our minimum value is negative 2 over square root of 3. So now for number 3, our function is f of x, y, z equals x plus 2y. And notice now we are given two constraints. So we have to find the maximum and minimum values of the function within both of these constraints. So the first one is x plus y plus z equals 1, and the next one is y squared plus z squared equals 4. So the formula is going to be a little bit different when we set up a system of equations. So f sub x this time is going to be equal to lambda times g sub x, the same thing, but now we have to add mu times h sub x. So let's just have x plus y plus z equals 1 be our g function, and then y squared plus z squared will be our h function. So if that's f sub x, then f sub y is going to equal lambda times g sub y plus mu times h sub y. And so lambda and mu are both variables, and obviously f sub z is going to equal mu or lambda times g sub z plus mu times h sub z. So let's go ahead and first find f sub x. So f sub x is going to be the partial derivative of the function with respect to x. That's going to be 1. Now 1 is going to equal lambda times g sub x. Now g sub x is also 1 plus mu times h sub x. Now the partial derivative of this function with respect to x is going to be 0, since there is no x variable. So that will cancel. And so we're left with lambda times 1, or lambda, equals 1. Now for the next one here, f sub y. Now f sub y is going to be 2, so 2 equals lambda times g sub y is also 1, plus mu times h sub y, so h sub y will be 2y. Now realize that we can substitute in lambda equals 1 into the other equation, so 2 equals 1 times 1, which is 1, so then 1 plus mu times 2y. Go ahead and subtract over that 1. 1 equals mu times 2y. Then I can go ahead and solve for y. So I'm going to go ahead and divide over the 2 mu. So then 1 over 2 mu equals y. So now for the last equation here, f sub z, let's go ahead and find that. So f sub z is going to be 0, because there is no z variable in the original function. Now lambda, we get that, times g sub z. Now g sub z is going to be 1, plus mu times h sub z, which is 2z. Once again, we can substitute in 1 for lambda. So then 1 times 1 is 1. So 0 equals 1 plus mu times 2z. Go ahead and subtract over that 1. Negative 1 equals mu times 2z. If I go ahead and substitute or solve for z here, z will equal, now I divide the 2 mu, so we get z equals negative 1 over 2 mu. So now, given what y and z equal, I can go ahead and substitute both of these into the h constraint. So let's go ahead and do that. Now y squared, so we have 1 over 2 mu squared, which is 1 over 4 mu squared, plus z squared, which is also 1 over 4 mu squared. Since negative 1 over 2 mu squared is that. That's going to equal 4. Since they're the same common denominator, I can go ahead and add the numerators. So 1 plus 1 is 2. 2 over 4 mu squared equals 4. I can simplify that to 1 over 2 mu squared equals 4. Now in order to solve for mu, I'll go ahead and swap the places of these two terms. So then we'll get 1 over 4 equals 2 mu squared. Now go ahead and divide over the 2, so 1 over 8 equals mu squared. So then that leaves us with mu equaling plus or minus the square root of 1 over 8. Now, square root of 1 over 8 can be simplified into 1 over the square root of 8, and the square root of 8 can be simplified into 1 over 2 times the square root of 2. So then we'll get mu equals plus or minus 1 over 2 times the square root of 2. So now, using the information that we got for mu, we can go ahead and substitute in both for y and z to find what y and z equal. So let's go ahead and first substitute in mu when it's positive 1 over 2 times the square root of 2. So when mu equals positive 1 over 2 times the square root of 2, let's go ahead and substitute in for y first. So y is going to equal 1 over 2 times mu, which is 1 over 2 times the square root of 2. The 2's will cancel, so 1 over the square root of 2 is simply just the square root of 2. So y is going to equal the square root of 2. Now the same thing with z here. Since z is just y just with a negative 1, then we'll just have negative square root of 2 as our z value. So now in order to solve for x, we need to go to the g equation, so the g constraint here, and then we can go ahead and solve for x. So x plus y, which is square root of 2, plus z, which is negative square root of 2, equals 1. Those will cancel out, so x will equal 1. So that's going to be our x value. So in coordinate form here, it's going to be 1 comma y, which is square root of 2, comma z, negative square root of 2. So now let's go ahead and find what x, y, z equal when mu is negative 1 over 2 times the square root of 2. So let's go ahead and first plug it into the y equation here. So then we get 1 over 2 times mu, which is negative 1 over 2 times the square root of 2. The 2's will cancel, so 1 over negative 1 over square root of 2 is going to be negative square root of 2. So that's going to be our y value. Y is going to equal negative square root of 2. Now if we plug in mu to the z equation, obviously z is similar to y just with a negative. So a negative times a negative square root of 2 would just be a positive square root of 2, so that will be our z value. And so now let's go ahead and find the x value. So looking at the g equation here, x plus y plus z equals 1. X plus y, which is a negative square root of 2, plus z, which is square root of 2, equals 1. Square root of 2's will cancel, and so x will also equal 1. So if I go ahead and write this in coordinate form, we'll then get x value of 1, y value of negative square root of 2, and then we have the z value of square root of 2. So now let's go ahead and plug both these coordinates into the original equation to find our maximum minimum values. So if I go ahead and plug in the first one here, we have x, which is 1, so 1 plus 2 times the square root of 2. And then if I go ahead and plug in the bottom coordinate here, we get 1 minus 2 times the square root of 2. So obviously the top one will be our maximum value, and the bottom one will be our minimum value.